small one, but now I'm scared. Looking at you, trying to see your stalling. Ooh, one hesitant step ahead. You're not a small one, but now you're scared. Looking at you, trying to see where you're crawling out. Emergency, oh.
I came all the way here to Israel to talk about how to build a scalable Git backend, which is kind of weird because like most people just don't give a shit about how to build a scalable Git backend unless you are trying to launch a GitHub competitor. In that case, please don't do that. That would suck. That would be terrible. But most people just don't need the infrastructure or the knowledge to build a huge installation of Git on their servers to serve clones to thousands and millions of people. So why am I talking about this today? Well, this is the story of how we began with GitHub, how we built the backend for GitHub over the years. And I think it's a very interesting story. Like, even if you don't actually have a Git backend in your server, like you probably don't, just the story of how we tackle these hard problems, I think it's worth telling. I think you're going to find here that's something that's actually interesting when it comes to a general insight into developing a complex backend for a huge web application. So hi, my name is Vicent Martí. Most people call me VMG. I'm VMG on Twitter and GitHub too. I've been at GitHub since the very, very early days, and I work on the GitHub systems team. The systems team basically takes care of all the infrastructure behind GitHub.com, you know, the actual backend code. We usually write C, sometimes we write Ruby, sometimes we write C++, but mostly C. Like most of the infrastructure behind GitHub is written in C. So since the early days, I don't know if you remember this, but GitHub launched with a very, very humble approach. The first version of GitHub that came out when it was still in beta, it had this slogan that says, Git hosting no longer a pain in the ass, which is a slogan I really like. I mean, it feels sincere, it feels honest, realistic, but it could be even more sincere. Like, it could be like, no longer a pain in the ass for you, but not for us, because Jesus, like if you imagine like the pains we go through like every single day to make this thing work, like if I've ever met the guy who invented Git, I will just, oh God, it's so bad. It works so terrible. The issue is that
He's supposed to live in California, ain't he?
yeah, I should probably go up and beat him up, but no, I'm kidding. Because hosting a Git repo itself is very easy, right? Like, you just grab your Git repo, the what we call a bird repo, the contents of the repo, you put them on a server somewhere, and you just punch a hole to that server, like through SSH or through HTTP, and people can just clone and push and pull from the repo. Like, that's very easy to do. That's very straightforward to do. But what it gets hard very easy is when you're actually trying to like add some value on top of that Git repo. Like, if you want to show something interesting on the website regarding the Git repo, if you want to show like the commits on the repo, the files on the repo, on the website, it gets very, very hard because there is no programmatic interface to access the Git repo. So in the beginning, since our stack was basically Ruby and Rails, we wrote a small wrapper called Grid that was basically that, a Ruby interface to a Git repo. So Grid was very straightforward. It was a Ruby library, and you would just like pass it a path to the file system to a Git repo, and it was capable of opening the repo and reading things like the commits on the repo, the history of the repo, the files on those commits, and all those things. So at the beginning that was enough for us because basically we could just like grab one virtual machine and put our main Rails application, because GitHub.com is still a Rails application. We could just put that on a virtual machine somewhere and have Grid on the same virtual machine and have a lot of repositories stored in the file system in that virtual machine. And that worked very well at the beginning, but as people say these days, that's not really web scale because it's just a virtual machine. So we ended up like to the point where the Rails app was serving so many requests that we had to use more than one virtual machine. So we had an issue, like we now had several virtual machines, and every single virtual machine had the Rails app serving web requests, but we didn't know where to actually store the Git repos because we needed all the Git repos to be on the same place so they are synchronized. If you keep different Git repos on every single virtual machine, that doesn't really work with load balancing because you never know where you're gonna hit. So the easiest way we found to tackle this is to use GFS, Global File System by Red Hat Global File System, which is a very straightforward way. It lets us mount the same global storage machine into every single virtual machine with the Rails app. In that way, we could actually see all the repos on every single machine on the file server, on the file system, mounted like a local mount point. So that way we didn't have to really change the Rails app. We could just continue using Grid, and we could just open those repos on the file system without having to consider the fact that they are over the network, because GFS takes care of abstracting away the network part, and it just shows the repos on the file system. This worked for a while, like about 6-8 months. It was working out pretty well, but it reached the point where we had so many virtual machines with so many Rails apps on every virtual machine that a single storage backend wasn't working enough for us. And like so many other Web 2.0 companies, like we got to the point where Rails was making us slow. But in our case, it was more literal. Like it was Rails itself that was making us slow. Let's just move the Rails to GitHub, and that basically tripled the amount of visits we had like every month. It was thousands and thousands of new people opening pull requests, like sending pull requests to Rails, and it was really making us slow. Like we were not prepared to have that amount of traffic like every single day. So it was a nice thing to have. Like it's a nice problem to have, like being too famous. But it was taking us down. It was a huge investment in time. It was a huge amount of traffic that we were not expecting, and we didn't know how to cope with that. So back then, we already have enough traction. We had enough users to have some money saved up, so we could actually move on to use real hardware to solve these problems. So we went ahead and we bought like real hardware, real machines. We started with 4 front-end machines, like good machines, and 4 file servers who will store the Git repos, and a separate machine for the database. And we had a problem because now we have like several front-end machines who run the Rails app and serve the web request, and we had several file servers who store the Git repos, but we didn't know, like, when you hit a front-end machine, how do you go to the file server to fetch that Git repo, right? So we came up with an idea. We call it Smoke, because it's like a cloud, but not quite, and kind of bad. I'll tell you guys how this works. This is going to make perfect sense in just a moment. Just let me explain. On the right, we have BERT, which stands for the binary Erlang term. It's a serialization protocol based on Erlang, the language, which basically takes the way that Erlang encodes data in memory and just sends it over the wire. So it's a very efficient compression of, it's like a message pack, or you would say like JSON, but binary. On the left, we have Ernie, which is not an acronym. We just thought it was the right name to give it. It's the web server written in Erlang that is capable of spawning processes in other languages. In our case, we have Ernie as an endpoint. It would just spawn Ruby processes to actually run a Ruby code for interacting with Git. So the overall architecture looks something like this. We had a front-end machine that used BERT. And when you actually hit a front-end machine, and we had to like look up commits or look at the history of a repo, we just did a monkey patch on the Rails app itself without actually changing the code. And every single time you went into Grid on the main front-end machine, it would just automatically serialize the request and just route it through Chimney. Chimney is a separate machine. It's based on Redis, and it takes care, like the name implies, it routes the smoke. So basically, when you hit Chimney with a special Git request, it will find out on which file server machine that Git repo is stored and route your request automatically to it. So what this means is that when you hit a request on the main file server, we find in what machine that the repo is stored, and we route your request automatically to it. So in the file server, we got Ernie running, and Ernie takes from Erlang the binary term that we get from the front end. It turns that into Ruby code, and that Ruby code runs Grid itself into the file server. So from that sense, we've managed to abstract the actual part of accessing the Git repo. It's still from the front-end machine, but we don't really change the code on the front-end machine. That means that the main Rails app hasn't really changed at all, and we have automatically abstracted away the network phase of this Git operation. So it can run on the file server, access the repo automatically on the file server, and bring back the data to the front-end machine without changing the code on the Rails app. This was very important to us because it means that while we were working on this stuff on the backend team, the people working on .com could actually continue building features, like adding new features, adding new functionality to the website without having to think about the backend, because the actual interface to the backend didn't really change. We didn't need to change the .com app to adapt to the new backend, which was very important because we could just keep shipping features like that. So this worked very well for us in practice, but eventually we reached the point where we had vertical scaling issues, which basically meant that the shit was low, right? So the main bottleneck we had was grid. Despite the fact that grid was written in Ruby, you know that Ruby is not the most fast programming language there is. It's actually pretty slow, it's pretty awful. So we decided to ditch grid eventually and move on to a solution based on Git itself, like the Git binary. Basically, when you would do a smoke request over the network and hit the file server, Ernie would just shell out and spawn a Git process to actually do the Git query on the file server. You may think this is slow, but it's actually not slow. Like, the only trick there is to shell out to the Git properly. Like, you cannot really spawn a shell every time you want to spawn a new sub-process, but if you use something efficient like POSIX spawn, which is the spawn API that comes with the Linux kernel, you can shell out to a real Git process in like 1 millisecond and do the actual Git request and bring it back to the front of the machine. So it was a very, very efficient way to do this. Like, just spawn the Git process, do the query, and return to the Ruby application. But it still had a lot of overhead because you actually had to parse. Like, it will return you text or we will return you blobs, and you need to parse that back into actual native Ruby structures that can be sent back to the front-end machine because the front-end is in Ruby. So by then, there were actually a lot of other companies that had basically the same issues trying to scale Git. And I like to explain it like the tale of Bobby, who is trying to make Git scale. Bobby works in another company, not in GitHub. I don't know which company it is. But one day he woke up and he went to his boss and his team. And he was like, guys. And his team was like, what? So Bobby said, I had an idea. I had a very good idea about making Git scale. And his boss was like, what is it, Bobby? And he said, well, why don't we take the Git binary, right? And we build it as a library. Like, we got this Git program that everyone uses on the command line. So instead of building that as an executable file, we just build it as a static library that we can link into a server process. So just get that and we link it into a server process. And Bobby's boss was very impressed. He was like, that's a genius idea, Bobby. You just make Git scale on your own. That's super impressive. So they did that. They just built Git as a library and just linked that into a Ruby process. And they run that, and it works very well. Until, you know, they actually had some metrics on their stack, and they saw this graph of memory usage over time. And memory went something like this. Boop, 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 boop. So Bobby's boss went up and like, you know, I'm not too sure about this because I'm not very technical, but it looks like we are kind of like a leaky memory, maybe. And you know, Bobby said, yeah, the thing is that we didn't really think about free memory. Because Git is a command line application, right? Git is an app that will run once, do something, and quit. So Git itself doesn't free memory because it's just going to quit afterwards it runs. If you build Git as a library and just keep it running on your same server process, it will just keep allocating more and more and more memory until it eventually quits. So of course, this is the kind of problem that we could very easily solve using CGI in 1995. But since we are in the present, that doesn't quite work out right now. So what we did was, somehow this is one of these things that just solve themselves. So many problems in computers had to just solve themselves. And we kept that running, and we saw the memory graph. And it looked something like this. Boop, 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 boop. And Bob's boss went to him, and he was like, you know, Bob, I'm thinking that this is fixed, but this looks like some very aggressive garbage collection right here. Because like there is a very serious deal. Like it almost looks like the program cached. And actually, yeah, the server died, right? It's basically what happened is that Git is a command line application, so it doesn't have built-in error handling. Like if you use Git and you try to look up a commit that doesn't exist or a history that doesn't exist, well, it just dies, right? It just quits the Git executable, it goes back to the command line. If you link Git into a server process and you try to look up a commit that doesn't exist, well, your server dies and you need to reboot it. So it's not a good idea to use that in production. So people back then had the same issues as us, and they had this very good idea. Like they said, since Git cannot really be linked into a server process, why don't we take this idea of having a library of Git, but we just write it from scratch, and we call it libgit 2. The 2 stays for this time we're going to try to free memory and see if it works. And it got traction. Like the people in core Git started working on libgit 2. They started like sending patches, writing a Git implementation from scratch that actually frees memory and has nice APIs. But then some people, actually there were people from Google, they woke up one day and they said, well, libgit 2 has a problem, which is that it doesn't have enough abstract factories. So they say, how can we fix this? And they say, oh, it's okay, we can use Java. So JGit was born. The J stands for Jesus. I can't believe we need that many abstract factories here. Seriously though, JGit is a very nice Git implementation written in Java from scratch, but we've never been able to use that in production, github.com, because we don't use Java github.com. No, it's like people. I say this, and people think like there's a brief timeline of how Java evolved. Like at the beginning, Java was new and super experimental, so people weren't really using it. And then someday along the way, it became too corporate, and people stopped using it because it was too corporate and all that stuff. And then someday Clojure and Scala came along, and people think that Java is cool again and all that. And when I say that GitHub doesn't use Java, like people think that we are stuck, like we are too cool to use Java. It's not true. Like GitHub is stuck like back in '94. Like Java is actually too new for us. Here's the thing. Like we got a very, very complex stack, a massive stack, and the more complexity you add to it, the harder it becomes to maintain. And if you really think that you understand the JVM, you're really either very smart or very wrong. And we are not that smart, but we don't like being wrong either. So we've always kept like a very, very Unix focus to a whole stack. Like we try to simplify as much as we can, and most of the time that means staying to C, staying to C++, and staying with languages that we deeply, deeply understand. You see, there's this quote by Ryan Tomeko, our director of engineering, that I really love. Says that some people think that GitHub is a Rails shop or even a Ruby shop, but it's not. Like GitHub is first and foremost a Unix shop, and everything else is just a detail. So for us, the JVM, JGit, this whole massive stack of garbage collection, all that stuff, it was never an option for us. So we had to take the plan B, and we went with libgit 2. And the fact was that libgit 2 was not quite ready back then, but we had this plan. Like they would just put this moron, basically me, working on libgit 2 full time until it's ready to actually use this in production. And while I went away to work on libgit 2, we had this other problem that well, we were growing very fast, we were becoming very famous, and there's this moment in this time of every startup, look at the time, it's not SQL o'clock, we gotta go upscale, right? And I don't know why, but people really wanted us to like go upscale with NoSQL and everything. Like I remember a year ago, I was in Iruko in Amsterdam, giving a talk about our backend too, and this guy came up to me and he was like, you know guys, I really, really like GitHub, but I've always wondered, do you guys even Mongo? I'm like, that's not a verb. That's not an actual sentence. That's not a thing. Like, okay, so here's the problem. That there was a blog post a while ago. It was like, Git the NoSQL store. Like, Git is like a NoSQL store, whatever. It's not. Let me give you a brief introduction of how Git works. This is the old logo that Git had at the beginning. If you look at this logo, like I don't think it's a particularly good logo because it doesn't really tell you much about Git itself. Like if you look at the logo, you can think that Git is made of like poor design choices. That's what it's made of. That's why I'm so happy with the new logo that my friend Jason Long did for Git. It's very nice, like it's very well designed. But what I really like about it is that it gives you a very strong hint about what Git is about. Git is about graphs. Git is a DAG, it's a directed acyclic graph, and it's the way that it stores all the information inside the repo. It stores it in a graph. So when you got like a working directory with your files on it and all that, and you do a commit with that, what Git actually does, it builds a tree in a graph about your working directory. Like you got this tree data structure that has pointers to subtrees that are the subfolders, and every single file points to a blob, which contains the actual contents of the file. Unlike that, when you do a commit, you got another data structure, which is the commit itself, which has a pointer to the tree, and metadata like the author, the time when the commit happened, the commit message, and a parent, which is the commit that was before that commit on your repo. So like that, Git actually builds a graph in the file system with the structure of your repo, the story of your repo, stored like an actual graph representation. Now, this is very convenient if you're trying to do something easy with Git. Like, if you want to go show like a commit on a website, you just go and you grab you get the SHA-1 of the commit, you fetch it, you bring it back, and you show it on your website. That's very easy to do. But if you're trying to do something slightly more complex, like showing the history of your repo, like the actual branch history, it becomes so expensive. Because to show the history, like you only know the tip of your branch, you know the tip of the master branch, and you can go to your file server, fetch the tip of the master branch, and bring it back, and then you can parse it, and then you see what's the parent, and when you know the parent, you go back to the file server, and you fetch the parent, and you bring back the parent, and you basically want to kill yourself, because you need to keep doing round trips until like it's a little known torture method. It's called death by round trip. And it's very painful. Like if you actually want to show a history of 1,000 commits, you need to do 1,000 web requests to the file server to fetch 1,000 commits because it's a graph. You don't know the full structure. You only know every single link along the way. And of course, if you're trying to do something more complex, like for instance, showing the last commit that touched a folder on your repo, that gets impossibly complex, because to find the last commit that touch a folder, you need to fetch every single commit on the repo and see which ones actually touch the folder. It's so incredibly expensive, and especially if every time you want to fetch a commit, you have to actually bring back a web request to the file server to bring back the commit. And the other issue we have, like we could work around this if it meant like actual benefits, having this distributed architecture, but it really doesn't, because Git doesn't give a shit about cap. That's the fact of it. Like to do an actual complex query in a Git repo, like something like the Linux kernel or WebKit or something like that, you're gonna need by average like 1 million hops. If you do those 1 million hops on the file system, that's reasonable. If you do them over the network, you're dead. It's a 1 million network requests, you cannot do that. But here's the issue. How many hops are needed to actually make that query succeed? You need a whole 1 million hops to make the query succeed, because if you miss a single one, the query fails. You cannot do 1 million round trips of the network and expect every single one of them to succeed. And as soon as one of them fails, your query is over because you don't really have the information you were looking for. So if we wanted to distribute this across a network and have enough redundancy to make sure that a query never fails, that a hop never fails, well, we would need like a metric shit ton of replicas to actually make sure that even if one of the machines goes down, the query can still succeed, because there are so many hops to do there. So we could definitely go ahead and fix this, but we're not going to do that. Because over the years, like libgit 2 has gotten to the point when it's very much ready to be used in production. And the approach we took over the last year is to switch over to a new design called Git RPC, which is basically less. It's basically everything we wanted, but it's less. Git RPC follows the same design as Smoke, but just simplified. We've removed all the Erlang from the stack. We've removed the custom serialization. We only have like a Ruby daemon that links Rocket, which is our Ruby wrapper for libgit 2, and libgit 2 itself running on a machine at any single time. So it looks something like this. Basically, we just added Git RPC daemons to our file server machines, so when you do a small request, we can just hit Git RPC directly and bring this back to the front end without having to go through Smoke, without having to go through Erlang, without having to go through Ernie or anything like that. And the big thing is that we actually still have Erlang on the stack, because there are older commands that still go through Grid, through the old Smoke pipeline. So what we did is that we just keep the whole website going through Erlang, through Grid, through the old pipeline, and all the new features we implement for GitHub.com, they go through Git RPC, the new stack. And slowly but surely, we keep moving over, porting all the old features to use Git RPC too, until we will get to the point where all this complex stack is gone, and we only have Git RPC on the client and Git RPC on the server. We've totally killed Erlang. We only have Ruby and C left, and this new design, this new architecture, is up to 50% faster, and it has like 100,000 lines of code less than the old one, which is quite an accomplishment. It's everything we wanted, and I also understand that it's not revolutionary, it's evolutionary and kind of disappointing. Like, it makes for a pretty fucking boring talk because there is nothing exciting here like NoSQL or distributed things or anything like that. But it's worked out surprisingly well for us. Since day one, at GitHub, we've had to tackle very, very, very hard engineering challenges. Things that have never been tackled before because nobody has hosted as many repos as we have. Nobody has worked with Git at the scale we have. We've had to invent things that just didn't exist before that. And we had to do that with a very, very tiny team because we really cared since day one about not growing our team too fast, about not going crazy with hiring. And we had to tackle that with very, very little money because at the beginning we were bootstrapped. We didn't have any real income, only what the customers paid us. So all this innovation, all this complex stack, all these designs, we tackled them by basically using the most reliable tools we know. And by reliable, I mean reliable, like things that we have used for years and years and years before GitHub, and that we know that they work well and that we really understand how they work. We also solve all this by always challenging ourselves to build the simplest thing that works. And not because this is easy, because you've seen that this new design, gRPC design, took us like a year and a half to implement, and it does the same thing it did before, just slightly faster. And with less code. So it's not like a huge improvement, but it's faster and simpler, and that's everything it means. It's also harder to implement, but that's what matters. It matters that it's simpler and it has less code than the old version. And for us, what really matters since day one is innovating where it really matters. Like, it seems that these days that there's so much fuss going around regarding like NoSQL and data stores and Go and Node.js and all that stuff. And since day one, we've always believed about building a revolutionary product instead of a revolutionary backend. Like focusing our development time on building features for the users instead of shit on the backend to jack off about, right? So, and when I say this to people, like they are worried, like they're like, but isn't this a kind of miserable? Like, if I don't think I could work in a company if I cannot use like Node.js or Go or Scala or Clojure or whatever is trendy right now. But it really isn't. Like, you may think that you need to use this new web language of the week to have fun doing your job. But I can tell you that at the end of the day, what really matters is like building a good product that changes people's lives and not thinking that much about what goes on the back end or what can make my job more fun. Because at the end of the day, what really makes your job fun, is going to places, seeing people actually enjoy using your product. So I can tell you that, yes, writing everything in C and using all complex stacks can get depressing sometimes, but I've really never had this much fun in my whole life. So I guess that's something. So thank you for your time. Thank you.